Now see, resistance depend upon what factors? First we'll see about how it depend upon dimensions. Dimensions is nothing but length and area of cross section of the conductor. For example, you can take this is a conductor which is having length L, area of cross section is A and length is L. Resistance formula we have like this: the resistance R is equal to rho L by A. Suppose if this area is circular portion, circular cross section, then you can write rho L by area we can write as pi R square. R is the radius of the circular cross section. So from this, how we depend upon length? Dimensions means length and area. So we can take how we depend upon length. R is proportional to length. So from this what you can write? So here we can write R1 by R2 is equal to R1 by R2 is equal to L1 by L2, and percentage errors if you want, right? Delta R by R into 100 is equal to delta L by L directly proportional into 100. If you get percentage change less than 5%, we can use this formula. Now how we depend upon radius depend upon area of cross section. Area of cross section nothing but R is proportional to 1 by A, inversely proportional. Otherwise you can write inverse proportional to R square. Radius of cross section, that is area of cross section. So from this what you can write? Suppose keeping length constant, only area changes, we can write like this: R1 by R2 is equal to A2 by A1, which is equal to R2 by R1. Of course square is there, otherwise whole square we can put. So because area is equal to by R square, so we get like this. What do you get? Percentage error. Suppose percentage error in the resistance delta R by R into 100. We can write inversely proportional, that's why we can write minus. It is not errors. So percentage changes we are calculating, not errors. So that's why denominator means you must take negative sign there. That is delta A by A into 100 inversely proportional, that's why you get minus. Otherwise, if you want to write in terms of radius terms, that you can write minus 2 whole square is there, no? That's why 2 delta R by R into 100. If percentage change is less than 5%, we can use this. So how resistance depend upon dimensions of the conductor? This is the relation we get. So here, keeping area constant, only length changes, we can use this formula. Keeping length constant, area changes, use this formula. Suppose now what happened, and we are taking a conductor which is having dimensions area of cross section A, length L, and mass M, density D. Now what happened, this wire is stretched in case of stretching. So how we depend upon length? One case is there, area keeping constant, and the second case length keeping constant. Now if you keep mass of the material constant, if you are stretching the wire, or this total wire is melted, total conductor is melted and recast into a new type of wire, then how we depend? Suppose if it is stretched, so you see resistance formula R is equal to rho L by A, and here wanted we can multiply with L and divide with L, that what you get rho L square by area into length, what you get? Volume. And volume we can write L square, volume we can write mass by density, density can write in numerator. Now on stretching, the wire are melted and recast into wire, which factor changes means resistivity not changes, density not changes, mass also constant. So here R is proportional to L square, R proportional to L square. Where we can, there R is proportional to L, area of cross section is constant and length increases, what happened? That. And here stretching means simultaneously what happened, when length increases, area of cross section decreases. In that case, we can write like this. From this, what you get? R1 by R2 is equal to L1 by L2 whole square we get. If you want percentage errors, if you want to write percentage errors, delta R by R. Delta R by R into 100 is equal to 2 into delta L by L into 100 we get. Same case if you do for area. Suppose here, in this case, we can take here R is equal to rho L by A. What if you multiply with area and divide with area, A square we get. So rho L into area is volume by A square. So nothing but rho V we can write as mass by density into A square. Otherwise this formula we can write like this, rho M by density, area we can write pi r square, so pi square r power 4 we can write. From this what you can conclude. So if a wire is stretched, the area of cross section decreases. In that case, r is proportional to 1 by a square, proportional to 1 by r power 4. Remaining all constant. For given wire, mass, density, resistivity, density are constant. So it depends upon area or radius here. So from this what you can write, r1 by r2 is equal to, what you can write, a2 by a1 whole square, or otherwise r2 by r1 whole power 4. If you want to write percentage changes, how to write percentage changes here? That equation I'll write here. This equation I'll write there, tops. Here we'll see, that is delta R by R into 100 is equal to area inversely proportional, that's why I get minus, whole square is there, 2 into delta A by A into 100. Otherwise, if you want to write in terms of radius of cross section, that is R also inversely proportional, but 4 is there. So 4 into delta R by R into 100 we get. Like this we get relation. So both cases are how resistance depend upon the dimensions only, but this case is when first R is proportional to L and where area of cross section constant, and R is proportional to 1 by A when length is constant. Suppose in case of stretching or recasting into other wire, use that case. It's R is proportional to L square and R is proportional to 1 by A square. Percentage errors. When we can use these 4 formulas, percentage errors formulas, when they give a percentage error less than 5%, then only we can use. Let's see the second case, how resistance depend upon nature of the material. Suppose you can take a conductor which is having dimensions length L and area cross section A. So resistance is equal to rho L by A formula is there. Of course, resistance depend upon length, area cross section, and it depend upon nature of the material. Rho represent nature of the material. Rho is nothing but resistivity or specific resistance. How they define resistivity? We can write rho is equal to Ra by M. How they define resistivity? It is the resistance of a conductor which is having unit length and unit cross sectional area. What are the units you see here? That is the resistance ohms. For area, meter square by meter is the length. So ohm meter is unit of resistivity or specific resistance. So here resistance depend upon what factors. If they ask, then we can write resistance depend upon length, area of cross section, nature of the material, and temperature. We can write 4 factors. Of course, impurity also there, 5 factors. And on what factors resistivity depends means it is not depend upon length and area of cross section. Why? Because here resistivity is the proportionality constant between R and LA. So here it is not depend upon length and area, but it depend upon nature of the material and temperature. About temperature we'll discuss later. Now we'll see about nature of the material only. So what is the resistivity formula? We have one relation, sigma conductivity is equal to 1 by rho, which is equal to mu Ne. Mu is mobility of the charged particle, and Ne is a number of free charges, number of free electrons per unit volume. E is charge of the electron. You see here Ne is more, rho value is less. Rho is less. Ne is more means the materials which are behaves like good conductors like copper, silver, gold. These are good conductors. Those are having number of free charges more. Resistivity less. Resistivity less means resistance also less. Those are good conductors. Suppose you can take bad conductors means insulators, rubber, pure water, and glass. These type of material are bad conductors. Their number of free electrons are less. Number of free electrons are less means resistivity is more. So resistivity more means resistance also more, like that, and resistance depend upon nature of the material. Also third case, how resistance depend upon temperature. Suppose you can take conductors. So a conductor, some current is flowing from one end to other end of the conductor. Current flow nothing but flow of charges. Suppose electrons are moving like this. When electron moving from one end to other end, it may take collision with the atoms or other electrons also because of random motion. So it may take a number of collisions inside the conductor and finally it comes outside. Due to these collisions only, that conductor offers some resistance, that only what we call electrical resistance. On increasing temperature, what happens? This number of collisions increases. Because of that, the conductor offers more resistance. So in case of resistance, how resistance changes according to temperature means R is equal to initial resistance is R naught at 0 degree centigrade. You can take R naught into 1 plus alpha T. T is at any temperature. Alpha is temperature coefficient of resistance. Alpha temperature coefficient of resistance. And how we get alpha value from this equation? Alpha is equal to RT minus R naught by here R naught into T. We can write like this. Suppose at two different temperatures, if you know, suppose R1 is a resistance at temperature T1 and R2 is a resistance at temperature T2. So here for metals or for good conductors, resistance is proportional to temperature. So from this what you get? Alpha is equal to, that is R2 minus R1 by R1 T2 minus R2 T1 we can write. Temperature coefficient of resistance alpha we can write like this. If you know in resistance initial at 0 degrees and at particular temperature T, we can use this. At two different temperatures, if we know T1 and T2, R1 and R2 are resistors, then we can use this formula. What are the units of alpha? Per degree centigrade. Per degree centigrade. It is just like a linear expansion coefficient in solids. Here temperature coefficient of resistance. In case of conductors, this alpha value is positive. Conductors having positive temperature coefficient. Same thing for insulators also. Conductors, insulators, in both cases we can write formulas like this. For example, if you take a resistivity or resistance versus temperature, if you observe the graph, for copper we are getting like this. For nichrome we get like this. Of course at 0 degree centigrade we can't say resistance is 0, thus we get intercept here. This is R naught. At a particular temperature T, that resistance is R. This is for copper, this for nichrome. Here straight line we are getting, so for nichrome it is a better formula when compared to copper, because here temperature is directly, resistance is directly proportional temperature, that's why we can use this. But overall, almost here also, copper, in case of copper, are good conductors, gold, silver, all are good conductors. For conductors, how resistance changes, if temperature increases, resistance also increases. But in case of semiconductors, we are getting graph like this. Suppose you can take silicon with temperature, the graph we are getting like this. You know, silicon is a semiconductor material. So for semiconductor material on increasing temperature, resistance decreases. Reason, we know silicon or semiconductor material having valency 4. To form stability, it may covalent bond with neighbor silicon atoms. By giving small temperature, what happens? Those covalent bond breaks and electrons get free. If you have more number of electrons, what happens? Resistance R is equal to rho L by A, and sigma is equal to 1 by rho is equal to, we have Ne mu. Number of free electrons are more, resistivity is less, so resistance also less. In case of semiconductors, on increasing temperature, resistance decreases. There we have negative temperature coefficient. For conductors and insulators, resistance increases on increasing temperature, so it has positive temperature coefficient of resistance. For semiconductors, on increasing temperature, resistance decreases, so it has a negative temperature coefficient. How resistance changes? In the same manner, resistivity also changes. Suppose in place of RT, what you can write? In place of RT, I use resistivity, rho T is equal to resistivity at 0 degrees into 1 plus alpha T. Otherwise, here alpha if you want, that is resistivity at T2 degrees centigrade minus resistivity at T1 by rho 1 T2 minus rho 2 T1, we can write. Of course, for this also, and units are per degree centigrade. Here also what you get, rho T minus rho naught by rho naught into T we can get. So this how resistance changes with temperature. If they get two different temperatures means how resistivity changes. This formula useful for conductors and insulators. For semiconductors, we are getting here negative sign, minus we are getting. For semiconductors, what you can write? Here, for semiconductors, rho naught into 1 minus alpha T we can write. Because on increasing temperature, resistance decreases there. It has negative temperature coefficient. Now see some applications, how resistance depend upon temperature. Suppose if you draw a graph between current versus potential, IV characteristics of ohmic conductor. Ohmic conductor means you know, and a graph it will be a straight line passing through the origin, and this is the angle theta. The slope of the line M is equal to tan theta is equal to change in I by change in V, nothing but it is reciprocal of resistance called conductance, which is equal to R. From this what you can conclude, if the line make more angle with respect to x-axis, that has less resistance. Suppose you can take two lines we have, and first conductor C1, second conductor C2 is there, graph like this. This is the IV characteristics. So which conductor having, and of course this has resistance R1 you can take, that is better, R1, and this has resistance R2. So this is theta and this is alpha and beta you can take. Here beta is greater than alpha. From this what you say, more angle means less resistance from this. So what you can write here, R2 is less than R1 we can write. Sometimes they interchange I and V value. V they took here and I they took there. Then in that case, slope of the line is equal to resistance. In that case, which is having more slope, that has more resistance. Suppose with changing temperature how resistance changes. That we'll see one application. For example, you can take any chrome wire having resistance R. So here current and voltage. Initially having slope some alpha you can take. On increasing temperature, what happened to slope? On increasing temperature, what happened to nature of the graph? It will be slope increases or decreases. That is his question. Nichrome means, so we know it is like a conductor only, and conductor or insulator. On increasing temperature, what happened? Resistance also increases. Here resistance increases means what happened to slope? Slope must decrease. So here we can write, and this is at T1 degrees temperature, and here if you draw a graph T2, and which temperature is more, and in which case resistance is more. This is R1 and this is R2. From this you can say R2 is greater than R1, then you can write T2 is greater than T1. If they give I and V, suppose they gave V and I, then we get reverse case here. Okay. Another example, suppose you can take, they gave a graph. They gave a graph like this, IV characteristics, one graph for conductor and other graph for semiconductor. On increasing temperature, what happened to slopes of the graphs? On increasing temperature. So you know, on increasing temperature for conductor, resistance increases, the slope decreases. So this graph is moving down like this. New position of the graph we are getting like this. But for semiconductor, what happened? On increasing temperature, resistance decreases. Due to that, what happened? Here slope increases. That graph is moving like this. Why? Because for conductors or insulators on increasing temperature, resistance decreases. But here what happened? On increasing temperature, resistance increases here. Here resistance decreases. That's why opposite side it moves. In some cases, here they gave angle something as 30, like that they gave. On increasing temperature, what happened? This angle increases, 30 increases. On cooling, what happened? This angle decreases, like that they ask. So these for both conductors, and this one is semiconductor, other is conductor. So in that case, they move opposite direction. Two resistors connected in series. R1, R2 are the resistors. Series resistance, so we have this formula in 10th also, R1 plus R2. R series equal to R1 plus R2. This formula look like C is equal to A plus B. In errors, what we are writing? C plus R minus delta C is equal to A plus B plus or minus delta A plus delta B. So from this, what you can write? Delta C is equal to delta A plus delta B. We can write like this. Similarly, by comparing these two equations, what you can write? Delta R series equal to delta R1 plus delta R2 we get. So divide with delta R series by R series we do. That means this one also can divide with same delta R1 by R series and delta R2 by R series. Now what you get? Delta R. We know one formula, alpha is equal to R2 minus R1 by R1 into delta T. Actually it is R1T2 minus R2 T1. If there is no much change in R1 and R2, take as R1, take R1 common. So alpha is equal to this, we can write as change in resistance delta R by and resistance same only R into change in temperature T2 minus T1 delta T we can write. From this what we can write, delta R is equal to R alpha delta T we can write. Just like a change in length of the wire, delta L is equal to L alpha delta T we can write in linear expansion. Similarly we can write here also delta R is equal to R alpha delta T. From this what we can write, delta RS is equal to RS into alpha series into delta T by RS is there. Only delta R value is this. Delta R1 what you can write, R1 alpha 1 delta T by R series. Plus what is delta R2? Delta R2 is using this formula, R2 alpha 2 delta T by R series we can write. Here R series get cancelled, delta T in all the terms get cancelled. What you get, alpha series is equal to R1 alpha 1 plus R2 alpha 2 by, here R series is LCM, same only. What is R series? Already we know R1 plus R2. R1 plus R2. If two conductors connected in series with different resistance and different temperature coefficients, then what is the temperature coefficient of the total combination, series combination of the resistors? That we can write like this. If two resistors are parallel, then how it changes? So formula 1 by R parallel is equal to 1 by R1 plus 1 by R2 is there. If two resistors are connected in parallel, then what is the resultant resistance? R1 R2 is there. Then we can write like this. From this, suppose I can take 1 by C is equal to 1 by A plus 1 by B. In errors and measurements, we have this expression also. From this, what you can write, delta C by C square is equal to delta A by A square plus delta B by B square. That is the formula we have. And from this, we need delta C by C is equal to delta A by A square plus delta B by B square into C. What is C from this? From this, what you can write, C is equal to AB by A plus B. That you can multiply here with. It is AB by A plus B. Okay, use the formula. This formula we can use for this. What is R parallel? What you can write? R parallel, you can write here delta R parallel by R parallel. See nothing but R parallel here is equal to delta R1 by R1 square plus delta R2 by R2 square in bracket is R1 R2 by R1 plus R2. That we get. Now what is delta R1? Delta R1 nothing but from this formula we can write delta R parallel by R parallel is equal to, that is R1 alpha 1 delta T. From outside we get R1 R2. So that is R1 square, R2 we can write here by R1 square plus, what is delta R2? Delta R2 nothing but from this R2 alpha 2 delta T, and outside R1 R2 is there. So R2 square R1 by here R2 square, and whole thing outside 1 by R1 plus R2 also there. Here after cancellation what you get here, delta R parallel. Delta R parallel means what you can write? That is R parallel into alpha parallel into delta T by R parallel, which is equal to here R1 square get cancelled, and here R1 plus R2 is there, that we can write here is R2 alpha 1 plus R1 alpha 2 here whole by, this is a common R1 plus R2 into delta T is there, delta T also get cancelled here. First we'll write, then we can take cancellation. So RP get cancelled here, delta T get cancelled, and what you get here, alpha parallel is equal to R1 alpha 2 plus R2 alpha 1 by R1 plus R2. Two resistors are in parallel, then we get a resultant temperature coefficient, we get like this. Color coding of resistors. What is color code of resistance means? That color code represents the value of resistance. Actually, resistance value is very small in size, a few millimeters, very less size is there. Due to that, we can't write any value on that. Even if you write, we can't see that properly. That's why to identify easily the value of resistance, they use color bands. Actually, 4 color bands are there, and suppose here colors they are using this black, brown, red, orange, yellow, green, blue, violet, gray, and white. And their values also given here. The black color band is there, 0, brown is 1, red is 2, orange is 3, yellow 4, green is 5, and blue is 6, violet is 7, gray is 8, white is 9. So these 3 bands represent with any of these colors. Those are representing the value of resistance. So here the 4th band is there. That 4th band represents quality of resistance or tolerance of the resistance. What is quality and what is tolerance means? You see that if this 4th band is golden color, then we can say plus or minus 5%. Or otherwise you can write, you can multiply total value with 10 power minus 1. Silver band is there, this one means that you can take plus or minus 10%, average quality. And gold means 5% good quality, and silver means average quality, 10 power minus 2 can multiply. Otherwise, if there is no band, only 3 bands they give and this band not given, then you can say poor quality, that is 20% variance is there. So suppose you can take here and you can think this first band is how to write the value of a resistance means. You can take a standard format, 2 boxes. These 2 boxes represent the value of these 2 resistors, these 2 bands into 10 power, and this box represent what is the value of 3rd band, plus or minus. This box represent what is the quality of the resistance. This is the standard format of writing resistance value. So first 2 bands represent what is the value of resistance. Suppose for example here you can think this is a red, green, and here blue, and that you take it as gold. Here gold you can think. Then what is the value here in place of red? What is the value there? You check. Red is 2. 2 you write here. Second one is green. Green is 5 here. And after that, 3rd one is blue. Blue is 6. So here in this box you can write 6. It means first 2 values directly we are writing. 3rd one is 10 power how much value? That multiplication of 10 powers, that it represents 3rd band. And 4th band, if it is a gold, gold means plus or minus 5%. So you can write here 5%. This total value is 25 into 10 power 6 plus or minus 5%. Otherwise this value only we can write like this also. 25 into 10 power minus 6, so plus 6. 5% of this total. How to calculate 5% of this total? So you can write first 25 into 10 power 6 into 5 by 100. 2 zeros get cancelled, here you get 4. and 25 into 5, 125. So 125 into 10 power 4 is the plus or minus value. So you can write, what you can write, 25 10 power 6 plus or minus that value, 5% of the total, 125 into 10 power 4 ohms we can write. So we can represent value of resistance like this with a percentage, or otherwise calculate the percentage, 5% of this total, we can add plus or minus, we can write like this. Like that we can represent with using color bands, we can represent the value of resistance. Suppose if they give reverse, they give other value. If they give numerical value, how to find colors, band colors. Suppose if they give 52 kilo ohms plus or minus 10%. So decimal point we can't take, that's why what you can write this properly, 5.2 into 10 power 3 plus or minus 10%. Write more properly, that is remove this point, 5.2 into 10 power 2 plus or minus 10%. Now what is the color codes? What about first band? First band 5 is there. 5 nothing but here green color. So first band must be green in color. What about second value 2? 2 nothing but red. This must be red. After third one represent what is the 10 power value? 10 power here 2 is there. So 2 means what you get? Red. After what about fourth band? Fourth band it will be depend upon 5% means gold, 10% means silver, and if no band is there means 20%. So here 10% given, so it will be silver. Like that we can calculate and we can check the bands. With the help of bands we can write the value also. For example, if they give a band like this, it is here violet, orange, red and no band. No band. Violet means first two values directly you can write. Violet means what is the value? 7. Orange means 3. Red means that third band represents 10 power how much value? 10 power 2. No band means you can say plus or minus 20% tolerance. Fourth band is plus or minus 20%. No color or no band is there. Fourth band is not there, only 3 are there. Then we can write like this. To remember these values easily, and we have a short word that is B.B. Roy of Great Britain has very good wife. So important letters here B.B. R.O.Y.Y and here Great Britain G and in Britain B and very B good G and Y means W here. So what are the values? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And for those three easy, gold means 5%, silver means 10% and no color means 20%. Now we'll see about superconductors. And normal conductor you can take, normal conductors and temperature, resistivity. Suppose on decreasing temperature, resistivity also decreases. We get a graph like this. This is the ideal thought what we are thinking. Temperature decreases, resistivity decreases. And not for semiconductors, this is about for conductors only. But actually experimentally what we get means resistivity and temperature. Of course up to a certain temperature it will be decreases like that only, but here at a particular temperature called critical temperature, all of a sudden the resistivity becomes 0, conductivity becomes infinite. Suppose for mercury it is having 4 Kelvin means very less temperature. So 273 minus 273 you have to do that for that. So nearly minus 270 degrees centigrade. So very low temperature. So at room temperature, and they are not showing this property, at low temperature, very low temperature, the conductors behave like superconductors. Why they call superconductors? If resistivity becomes 0, conductivity is infinite, and for a given potential you get huge amount of current, infinite current we are getting.
Even after disconnecting the battery, the same current is rotating for long period. Those type of conductors what we call superconductors. And where they use these superconductors means in electromagnetic train levitation they use these superconductors.